presentation to share?
Oh, okay. Sorry. Yes. Let me do that. Make you co-host. Okay. Now you should be able to share.
I'm gonna go to full mode. Okay, do you see it now? Just
Yes.
Yes,
Yes.
I would talk, let's say as we discuss, I would talk about condensed matter aspects of topological superconductivity and maybe review the status of a field and the problems why it works or or does not work, what is current challenges in the field which we're trying to address. Just a moment. Not used anymore to, it's like it reminds a little bit of COVID times. Next slide. So yeah, as you know, one of the motivation why topological quantum computing attracts attention is that this idea to use topological qubits. And let's say 10 years ago, it was, I would say, like a lot of excitement in the field that we can do it in condensed matter very quickly, let's say in terms of Majorana fermions. And this is a paper, I think, from Science 2016, which lists all platforms which are kind of on forefront of quantum computing. And of course, superconducting qubits made a lot of progress over these years. Also kind of trap ions, right? This is the platforms I think most probably widely discussed in the media. So they have also their own advantages and disadvantages, for example, in terms of size and speed, so how quickly you can manipulate these qubits, and there could be fundamental limits how about the speed of such computations. And let's say the field which is also familiar more to me is silicon quantum dots, or in general spin qubits, right? When you manipulate spin by local electric and magnetic fields. So far, I think the maximum amount of qubits, which was around 18, and they're not all entangled with each other. So the progress in this field was also made, also in terms, I think, of how many nines they can get is now, I think, 5 nines in spin qubits. But the problem there, for example, is how to realize long distance coupling. Right, and the idea of topological qubit was that all qubits which are listed before, right, they suffer from local noise, right? It's either quasi-particle poisoning or nuclear spins or fluctuations in the environment. And this is the source of errors why it's kind of difficult to go to more qubits or to have more nines. And the idea of a topological qubits that you can go to the totally new computational scheme where these local errors will be less important, right? And one of the kind of largest companies who got attracted to this idea is Microsoft, and they invest now a lot. They have huge labs. There's a lot of investment in this area, and unfortunately, so far, let's say if you ask me, I would say they did not observe yet qubit which they can manipulate, and but there could be, of course, like also definition what people call qubit, right? So let's say if you go to De Vincenzi criteria, it's not only that you should show that you have two-level system, you can show that you can need to show that you can initialize it, that you can read out, that you can measure, make superpositions, that you can kind of characterize your qubit in terms of T1, T2 times, right? And success rate. And this is, I think, definitely, let's say, if you would put such criteria when topological qubit is not yet observed, we did not know all characteristics or idea how to couple qubits to each other experimentally was not demonstrated. But still, kind of idea of topologies, condensed matter is interesting, maybe not only for quantum computation, but just in general to show that such exotic braiding statistic could exist.
I have a question.
Yeah.
So by the logical success rate, are these 1 qubit gates or 2 qubit gates?
I think here it was still a 1 qubit gate because a table from 2016. Of course, yeah, with numbers, usually like when you do a single qubit gate, it has much better fidelity than 2 qubits. So this,
Yeah,
I
yeah,
think,
sure.
it's
Oh,
true
okay.
for all
Okay,
qubits.
so these data are from 2016.
Yeah, yeah, exactly. I think now they have progressed to 5 nines, so they're kind
Yeah.
of, because as you know, for superconducting qubits, they run the first type of error correction schemes, and this is
Mm.
much better. But this is also I still keep, this is my old slide from I think from 2000 to show like how much progress some qubits made and
Mm.
how much, let's say, topological qubits, let's say, most probably what is written for topological qubits is still true.
Yeah. Yeah, that's
So.
right. Okay, great. Thank you.
But here it's like, of course, it's much better. But let's say take into account, let's say for quantum compute, if you want to do something useful, right, you need, I don't know, 10,000 millions of qubits. So from this point of view, to have now 2 qubits or 100 qubits is still infinity away from where you want to be, right? So this is unfortunate, I would say. It's still, so the idea, let's say, as I said, like of topological quantum computing is this different way how would you run physically your operations. So let's say if you want, let's say, easiest example, you have spin qubits, you have operation 0 and 1, you define as up and down. Obviously, you can make superpositions and you manipulate, let's say, if you apply magnetic field perpendicular to the axis around which spin is aligned, it starts to process, and this allows you basically to move on this Bohr sphere and go from North Pole to the South Pole, right? Just by flipping, if you know, let's say, how much magnetic field you apply and you can time it precisely, then in principle, you should be able to go from 0 to 1. But the problem that you have environment, so you have, for example, nuclear spins around, and they produce tiny magnetic field, right? But it sums up with the field you already have, and at the end you would never go exactly from 0 to 1, you would come to some vicinity of this 1 here. And this would be a type of error which you would observe, right? So. And this is a problem, let's say, for all qubits, like superconducting qubits, spin qubits, they're sensitive to environment. There's, of course, different ways how you can combat it, but you can never kind of precisely arrive to 0. You can only minimize these errors. And the idea of topological quantum computing, that we have this one idea that you have all particles that could be divided by bosons and fermions, right? And they described by the exchange statistics. So if you exchange two particles, you know that your wave function total picks up the phase, right? And this phase is fixed, there's no fluctuation. So this, let's say for boson, this phase is 0. For fermions, it's -1, so you can write this as a pi phase. And there's no fluctuations. As long as you know that you exchange particles, you know that you get this fixed phase, right? And the idea is now, of course, that getting a phase like 0 and pi is boring. And there's a particle which called anyons, which can take a value which changes between 0 and pi. So usually it's given setup is fixed, let's say pi over 2, 2 pi over 3. But every time you exchange these particles, you pick up this phase, right? And in addition, if you also would assume that the phase which you pick up also depends on the path. Let's say if you change particle 1, 2, and 3, so when you change 3 particles, they describe already not by phase, but by matrix. And you can think, okay, this could give idea how you can run topological quantum computing schemes. If you have enough, let's say if your phase is rich and your matrix non-abelian, so they do not commute, you can try to mimic all needed topological operations for quantum computing using this braiding. But for this, of course, you need usually to go to full quantum computing, right? You need to go to very exotic particles. So let's say not Maranas are not enough, parafermions not enough. So you need to go to Fibonacci anyons, and then they would have a powerful statistics to give you all operations. So in the initial phase, what people try to get now is Marana fermions. And here now one can say, even if you would get them, so you cannot run fully topologically protected quantum computing. So some operation would be still missing, and you can add them by coupling, let's say by bringing this particle together, making them overlap, generating standard system similar to the spin qubit. But of course, during this operation, you're not immune against environment. But the motivation kind of quite general to what we want to, where we want to go. Right, and the question, let's say, how to get these states, and the idea here it comes to the most kind of simple topological model we know, which is a Jackie-Rabi. So here we assume that we have just 1D system. We have a kinetic term. For simplicity, it's linear term, right? So in principle, you would have a spectrum, which is a Dirac. And now we open a gap in this spectrum by mass term. And we assume that this mass term can change sign. So at one, let's say, half plane it's positive and now it's negative. And what we generate, what we call in physics, we call it the domain wall, right? This interface between positive and negative mass. And what is interesting, let's say, when we can show that when you change, let's say if you look at momentum k equals 0, right? when the eigenstates of your solution at k equals 0 is eigenstates of Pauli matrix Ty, right? And they could be colored in two different colors, like blue and red, depending if it's Ty eigenstate plus or minus, and which of them is above or below. It depends on size of a mass. So if mass is positive, so the lowest eigenstate is -1. If mass is negative, the lowest one is Ty is equal to 1, right? So, and then you can say when you bring this interface of the domain vote together, the signs of a gap changes. And then what is interesting is that at this point where you change sign of a gap, you host a bound state. So in this one-dimensional system, this bound state sits exactly at 0 energy. And what is kind of interesting that it's stable, so we can actually perturb how we change this. So I can, in a kind of simple example, I assume that mass just changes as a step function. But what is important at the end is only asymptotic on plus and minus infinity. In general, we can find a general solution and show that it sits at 0 energy, independent of a mass profile, right? And this is what people kind of already associate with topology or stability. But you have kind of eigenstate, which does not depend on how exactly material parameter is changing. So it would not change if you change a mass. It would not change if you change also Fermi velocity. And this is kind of a first example of symmetry protected, in this case by chiral symmetry bound states.
Sorry, one question. What is the derivative of x?
Here it's just, we assume that we have a kinetic term, right? So this kinetic term would be hv Fermi sigma z k, right? So you have right movers, which would have positive velocity, and left movers, which are negative velocity, right? And this is characterized by Pauli matrix sigma z, right? Because in the spectrum, I need to have both branches of right movers and left movers, right? So right movers are described by, let's say, sigma z equal to +1, right? And when I have a positive dispersion, hv Fermi k, right? And if Fermi velocity is negative, then you would have opposite sign. So it would be minus hv Fermi k. This is what I have shown. I have not, but basically here the gap is already open. But before gap is open, you would have just a linear dispersion as a function of momentum. And because you have a one-dimensional system, if you would not have a mass, then you would have particles which have just linear dispersion.
But isn't it you can write a Pauli matrix all depends on x, two of them? I'm confused why you have all three. You have x and y and z.
No, maybe there's so tau z and tau y are labeled Pauli matrices. So in principle, most probably it would be less confusing if I would write here tau 3 and tau 2. Because with z and y, they have actually nothing to do with spatial coordinates. They just label Pauli matrices. So, and the sigma x is a derivative. So this is Hamiltonian. You have a system which depends on x coordinate. So you have 1D x coordinate, and this is a simple term of a kinetic. This is a mass term, and this is like, let's say here, my system goes, is a function of x.
Thank you.
But yeah, it's very confusing. Sometimes we call this Pauli matrices x, y, z, but yeah, 1, 2, 3 most probably would be less confusing here, but they have nothing to do with spatial. You also can make all types of confirmation. What is important here, that the gap is open, so you need to have two terms which do not commute with each other. So it's important you'll see that here you have a Pauli matrix tau z, and here you have a Pauli matrix tau y, so they don't commute, and that's why you have opening of a gap. But in general, it's kind of not important. Here I notice that I have here sigma x, but it does not matter what kind of Pauli matrices I chosen. So basically the idea that you want to have a gap, and to this gap you want to assign some sign of ordering of bands, and this ordering of bands changes as a function of a position, and this is what creates a domain wall. And the idea is usually why you have this topological protection. So what we call, now we divide all systems, let's say when we talk in condensed math about trivial and topological, so the definition that we would be interesting only in the system which have a bulk gap. So from beginning we assume that there's a gap. So if there's no bulk gap, in energy spectrum, then it's definitely not interesting for our purposes. And now the system which are gapped, we would divide on the trivial when you have just a gap and there's no bound states inside. Or maybe there are some accidental bound state, but in generally, let's say ideally we start with a case there's no bound states at all. Right? And then we go to the topological gap phase, and there we have again energy spectrum. We have a gap which is open here, like from here to here. So, and then we have a bound state at zero energy. And what is important here, that with zero energy, let's say if you look where this bound state sits, this bound state should be non-degenerate. So at each given point, you should have, let's say, one here, one here, one here, and they should not talk with each other. So spatial localization of this bound state should be much smaller than the distance between them. Right? And this comes to the idea, let's say if I would consider that I want to do this braiding and indeed move particles, exchange them, the condition would be that these bound states are very well localized. When I move them, they never come close to each other. So at any given space, I have only one bound state, or maybe nothing if it's far away from anywhere. But the idea is here that this is like trivial, no bound states, topological, you have one bound state inside the gap, right? And where the stability of this bound state in the topological system comes is exactly from the point of view, let's say usually you have some in the Hamiltonian, let's say if you work with superconductors, you have a particle-Hall symmetry incorporated. So Hamiltonian has a symmetry that if you know that you have solution at energy E, then you also know that you would immediately have solution at energy minus E, right? And this is kind of given by structure. Let's say it's the properties of all superconductors that solutions are coming in pairs. We call it a particle-Hall symmetry. But now, by some miracle, we assume that we have managed to find one solution which sits exactly at zero energy. And this is a single solution, right, miraculously. And then you can see what would happen if I would add some perturbation to the Hamiltonian, and I still keep this particle-Hall symmetry. When you can see that this state cannot deviate neither up nor down, because as soon as I would try to get it a little bit away from zero energy, right, it would go to finite energy, and then it obviously would need to have a partner, right? But my Hamiltonian is kind of well behaving, there's no singularity, nothing unusual, so it means by small perturbation, I cannot generate from one solution two solutions, right? And that's why if I have a single state at zero energy, I cannot split it away, right? It's kind of forced to stay there. And this is what we call is a symmetry protected. So all superconductors, let's say superconductors, they have this property to have a symmetry. And this is what kind of, let's say in a simple way, explains why these bound states afterwards would be stable against disorder. Just a moment, yeah. So, and this is kind of most probably the most intuitive explanation. Of course, one usually can calculate some topological indices and something complicated, but I think there's very intuitive explanation. Right, and if you go exactly to Majorana fermions, so it's still kind of a fermion. So it has, if you have two fermion, two Majoranas, right, gamma and gamma prime, they have a standard anticommutator. So if you exchange them, you just pick up a minus sign. But what is important, because Majorana, as I said, like it sits at zero energy and it's non-degenerate, right? But at the same time, we know that all solutions in the Hamiltonian, they come as in pairs, right? And the property of this Majorana fermions, what it means, it should be pair of itself. So gamma should be equal to gamma dagger, right? And that's why quite often about Majoranas, you hear that it's a particle with its own antiparticle, right? And this can come from this miraculous property that the operator is self-conjugated. So when we work, let's say, with Majorana fermions, well, in condensed matter, usually we would write wave function in the basis. And let's say if you choose a basis, let's say the first component is amplitude of being spin up, and now we spin down, and holes are conjugated. So first two components is electron, and the last two components are hole. Right? Then you can see usually, let's say, if you consider general state, that all these four components in wave function would be independent, right? There's nothing. But if you work with Majoranas and we have a property that gamma is equal to gamma dagger, right? Then we know that the upper component, the first component, should be conjugated to the third component, right? And the second to the fourth. And this is kind of already kind of restricts how your wave function could look like, right? So we don't have all 4 components independent, only first 2. If you know the first 2, you can, by this property, reproduce another one, too. And now we can calculate expectation values, like, for example, what is average spin, what is average charge, and you would find that due to this shape of wave function, you would always find that it's 0, right? And this is also kind of explains the stability, because the way usually we couple, let's say, to the particle is by applying electromagnetic fields. But if your average charge is 0, if your average spin is 0, it means the coupling constant is 0 and you cannot move. Right? And this is also like one of ideas where this kind of magic stability of Majorana fermions, white state spins to 0 comes. Right? And this is what I kind of try to emphasize before. So what we're searching for the system, we have a gap. And inside the gap, we have the 0 energy states. So that it stays at 0 is kind of not important. We just want to know that you have many, many states and they all stay at 0 energy. Such we can pick up, build up a degenerate subspace of low energy states. And we usually assume that the gap goes to infinity, temperature is much smaller than the gap. So we can focus only on these low energy lying states. And what is important, of course, you can say you can still take a quantum dots or trap ions or anything, and you can fine tune for ions. It's even easier, right? As soon as they're identical, you can also say they all at the same energy, right? So, but why would we not call them topological, right? But in this case, let's say if you fine tuned, when you know that if you apply any weak perturbation, right? If one of your ions sees a little bit different electric field, right? Energy is already shifted, and this degeneracy is gone. But for topological system, as I said, it's important that it comes from some miraculous properties of a Hamiltonian. So even if you add some weak disorder and weak perturbation, the degeneracy is kept. So you cannot, it's very difficult to lift the degeneracy. There's like 2 ways to lift this degeneracy. Usually either you need, because here the keyword I said weak noise. So what we say weak, it means it's much smaller than the gap. Right? So the gap is important parameter. So if you want to say like the topological system, how much you need to control your environment, up to the size of the gap. So that's why it's kind of important to find system where this topological gap as large as possible. Right? And to keep this, or another way is, I said, usually we assume that these 2 states are separated, right? Because the protection worked because my state was a single, right? But now if I would bring 2 states together and they start to see each other, they start to overlap, now they can split in symmetric, anti-symmetric combination, right? You would get, I don't know, one going to E, another to minus E, so symmetry is not broken, right? That's why one of the kind of conditions when we, let's say, generate in some 2D plane this bound states, we try to move them. And this is movement with code braiding. So we need to know how many times we exchange particles. It would be important that they stay away from each other. So this is also the condition. So it's important, let's say, and usually what is localization length of these bound states is given by gap. So larger is your gap, the more they're localized. So that's why gap becomes kind of important issue in this field. So any questions to this part?
Yes. Since you have braidings on your slide, you assume these are 2D systems in some sense, or?
Yes, because in 1D you cannot exchange it, right? Because if
Yes.
in 1D, this is what we kind of work in. Actually, with 1D system are very important in theory, because when we consider, for example, in strong interactions, right? And usually, let's say it's known that we have very good apparatus to describe interactions in 1D, but let's say we have huge problems to describe strongly interacting systems in 2D, let's say like a quantum Hall, fractional quantum Hall, for each filling, which is a fraction of the 5 theories of different origin, trying to explain what it is. And the idea, because it's very difficult to describe interacting system, for example. But why can we describe 1D system? Because in 1D system, if you have 2 fermions, they can never be exchanged, right? And then you can basically say, and the reality in 1D system, you don't work with fermions, you work basically with bosonic excitations. And then you can have all apparatus to describe them. And this is kind of nice, because in 1D, exchange is not possible if you strictly 1D. So that's why, let's say, if you have seen, let's say, Microsoft experiments, right, they work with nanowires, and you can say, well, what's the point? Because in 1D you cannot do it. But what you can do basically in this case, if you would consider when you have, let's say, so-called the T-junctions, right? Because when it becomes kind of every time for your physics, it's 1D system. But at the same time, so I can try to put, I can say, if you would generated something like this, right? Then you can start with, let's say, one fermion here and one fermion here, right? And then you can, let's say, you can now take this one and you could move it like this. Every time staying in 1D channel, and then you take this one and you move from here, right? And when you return. And this is a way how you can, let's say, with tin junctions, you can exchange them. So now if you would have a square lattice, then you can still do quasi-braiding, staying always 1D for properties. And this is kind of important.
Yes. Okay.
Because
And
at the
and that
moment,
you
let's
have
say
this
the
junction point does not matter at all. I mean, there's
no.
one point which is not 1D, but this is not important. I mean, it's important for what you explained, but for the particle, it doesn't care about this very
No, because
specific
let's
point.
say you kind of, at this point, when you kind of move, you have this structure, right? And let's say this part you can make with this leg is topological. And this is a trivial, but it has very large gap. You can put this gap, let's say, to infinity, right? And then it would not see it when you move through. So you can kind of make a smooth transition through it. But of course, let's say another question, let's say when we talk about braiding, I say, oh, I need to move with particles. The question, which kind of speed I can afford to move? So can you guess what kind of, how fast can be they moved?
Well, for me, no idea.
I think it's basically they have only one length scale. Here's the gap of your system, right? Because you know that you have in quantum mechanics, you have uncertainty, like delta T times delta E is h bar, right? So this gives you, like, if you delta E, I said you cannot have energy uncertainty larger than delta, because then you would excite it over the gap. That means when you move for particles, you need to move with length scale, which is h bar over delta. So your speed of movement should not be faster than this. And this is, again, kind of gives you idea why gap should be large. Right? Because every time you have a particle, it's kind of, you always assume that here, you always assume that you stay in the ground state. Right? And now if you have moved particles very quickly, there's always probability that you end up in the excited state. Right? And the only what kind of protects you not to end up in the excited states is that it's very far away from energy. So if your speed is enough, very slow, then you kind of, it's kind of a diabaticity requirement. And this is kind of, again, fundamental, because you can see now all problems, like, let's say you can ask, before I said, okay, superconducting qubits, they're not the fastest, or trap ions, right? They have fundamental limits that they are, when some people say they're large and slow, right? And this is set by superconductivity properties, let's say, in some cases. And here it would be exactly the same, because you have this gap. If it's superconducting and measure all topological, let's say Marana parafermions, they come from superconductivity, because this is what we need to have a symmetry, right? But with superconducting gaps are not very large, right? So then it means that it gives you like, and if you would do all your operations by moving, right? You have a constraint, you have a speed which is limited. You cannot go infinitely large. Right? So like operation in the nanoseconds are not on the table here, right? You need to satisfy this adiabaticity. And of course, like how much you need to move them also depends how far away they're from each other, right? And there's a kind of a constraint that you have the size of the particles, and you cannot come closer than this size, right? So it means like distance, you need to keep them far away from each other, which gives you kind of a size of 1 qubit. And then the speed with which you move is also not very fast. But there's kind of this idea that if you would do this stuff, then you would be protected from errors during this braiding statistics. However, this was kind of described. There's also one caveat in addition, is that we always assume that here we are at 0 temperature and we don't have, let's say, quasi-particles. And if one go to real superconductors, let's say quasi-particles are problems for superconducting qubits, there would be also the same type of a problem for topological qubits. Because you would assume that you initialized your ground state, you filled with states, and suddenly some quasi-particle comes, it changes your parity in uncontrolled way, you can get out of your computational space, and this would all result in errors. And let's say what we have discussed now, how Hamiltonian is constructed, it protects one from, let's say, noise from environment in terms of perturbation, let's say electrostatic fluctuations, nuclear spins, fluctuations of magnetic field, what anyway you have. So this is you protected, but you're not protected from quasi-particles. So because with many body stuff, these Hamiltonians do not know about. And this is, I think, sometimes maybe not fully communicated, at least like in the beginning of a field, it was not realized that it's actually also a huge problem. And there's, because here you have no more protection than superconducting qubits. So if you cannot get to low temperatures, then you have a problem. And what we know from superconducting qubits, that initial belief when you cool down superconductor, the number of quasi-particles should go to zero. But at some point, people cool down and it basically saturates and you cannot get rid of them. So this would be a problem also here in this stuff.
Maybe a quick follow-up question. What is the rate of these quasi-particle? I assume they are like a thermal anions. Is this the same thing?
I think one of them is a thermal source, of course, because as soon as you have a temperature, when you have a finite probability to be above a gap, and this is the source of quasi-particles, right? But there's also one of kind of sources which will establish this, because people will say, okay, when you cool down, right, and then it should go down, and you cool down, it's not getting better, you get on a constant. And one of the measurements which they did for superconducting Rabi, it basically comes from cosmic rays.
Mm-hmm.
So you have a bunch, and then you have a huge burst of energy, it breaks some Cooper pairs. You have a lot of quasi-particles. After some times you go and again. And this was measured basically when you take these superconducting qubit devices, which have very good sensitivity now, you put them somewhere in the cave in the mountains, and then you can see that this rate goes down.
Mm-hmm.
So it was again. So basically, the way I think it's also like nowadays, everything which exposes your qubit, you can sell as a detector.
Mm-hmm.
Right? So, because qubits at some point, let's say, also, as we know, let's say, or NV centers or atomic clocks, right? It's basically very sensitive qubits. So they can measure very small signal of disturbance from the environment. So there's also, I know many colleagues in the, let's say, also work with superconducting spin qubits, also measuring, let's say, even interaction like with dark matter. So because sensibility at some point gets huge, what can disturb your qubit. But in general, let's say it's always a trade-off when we compare different qubit platforms. So that usually you can see one tendency, right? You have a qubits which are very long cleave, like the T1, T2 times are very large. For example, trapped ions from the beginning, they had very good T1, T2 times. And let's say spin qubits, at the beginning they did not have such good times. Now kind of material is improved. And the trade-off is usually works like this. So if you have a qubit which is well isolated from environment, you get very long coherence times. But when you have a problems to measure it, right? Because measurement is also important during operations. Usually you need to do error corrections, so you always need to do measurements that you perform. But the problem is usually comes like a dual. Let's say if you have very good times, your environment somehow has problems to couple to your qubit, which is good, your qubit is protected. But when you come and you want to measure, and you also have a problems to measure, right? Because which channel would you use? It's difficult to find the channel which you can use in like in your lab as an experimentalist, but nature doesn't have access to this channel. Right? So when you have a qubits, let's say, which have, let's say, couple kind of have more disturbance from environment, right? They don't have such good characteristic, let's say, like in times of T1, T2, spin qubits, you need to manipulate them some sweet spots. But then you can make measurements much faster because it means you have a channel in principle to couple to the qubit. And this is, from my point of view, it's kind of a little bit also the trade-off between all these computational schemes. Because this would also be the problem, let's say, of topological qubits. You would say, okay, they're so well protected, environment cannot address them. How would you measure them as an experimentalist? Right? So you would need to bring them together, try to destroy, do some kind of projective measurements in order to know in which state your qubit is. And all schemes, they kind of run on the trade-offs of doing measurements, doing error corrections. And this is, I think there's no kind of a golden path. So that's why quite often what is important to characterize qubit is most probably not so much like T1, T2 time, so how long your qubit keeps its coherence, but how many operations you can do during this time. So more a number which is more saying, let's say you need to know how long your qubit live, and what is the time of your typical operation time, right? You divide, and this gives you number of gates which you can perform before it's dead. And this is much more saying number than the absolute scales for qubits. I mean, of course, like, let's say if you work with trap ions when these times are very long, then it's of course a problem, because if you have some, I don't know, computational scheme and you need to run, I don't know, millions of operations in each a second, even if you overperform classical computer in long terms, maybe you don't have such time to wait, right? Because what is important is not only scaling, but initial prefactor, which is determined by time scale of single operation. And this is another trade-off one needs to consider. So from this point of view, let's say with topological qubit, at least based on superconductors, they would not be the fastest one. Right? And another point, of course, also for topological qubits, one should consider, let's say, here, let's say, even if we realize it, and we would say when we, by construction, our system does not have any errors. But when you need to do operations, right, quite often you need to do measurements, right? And measurements, they would contain errors. So measurements, they would not be error-free. Because let's say, you couple to some spin qubits, you read out, you couple to some other apparatus, so you can assume, and at some point for you, for experimentalists, it would not matter if errors occur during the measurements or inside the system itself, right? It's just, you know that your final result is wrong.
So for topological qubits, do you consider the fusion of anions a topologically protected operation? Is it topologically protected? I guess that's what you do when you want to make a measurement.
Yeah, so usually what you would do, let's say you want to read out the parity of a state, right? Let's say you have, so in quantum computing with Maranas, for example, you have these two Maranas, right?
Mm-hmm.
And you have a fermion which they share.
Yeah.
Right? And this 0 and 1, it means this fermion occupied, the fermion is empty.
Mm-hmm.
Right? So when if they're far away and the state is protected, you have no way to measure it, because otherwise environment would measure it. So only what you can do, you need to keep bring them close to each other, right? When these two states starts to overlap, right? And they go at finite energy. And then there's kind of a way you can couple to quantum dots. You can have some dispersive. You can send a signal which would be diffracted differently depending if the state was occupied or empty. But as soon as you brought them together, the topological protection is gone in principle. So there's many other things which could happen during this time. You can now you're not protected from quasi-particles. You can lift, and these measurements would have its own errors.
Okay.
So during measurements, you can introduce when errors and anything else could happen.
Is there a way to do some kind of interferometry to measure the total charge instead of actually bringing those anions close to each other?
Yeah, I think like maybe you refer like now there's a kind of these experiments of Microsoft which does type of interferometry, right? So what they do is they take this one divider, right? You have Marana here and you have Marana here, right? And you want to measure the parity. But what they do is they bring like one large quantum dot, and this quantum dot couples on one end to left Marana, another end to the right Marana. And now what happens, that level on the dot shifts, because when you have two systems, they couple to each other, usually you have a shift in the energy. And of course, now with two Maranas, they talk with each other through this quantum dot.
Okay.
Right? So basically what happens, like now you have kind of circle, you put the flux through it, so this is your kind of way interferometer, but in order to pick up Aromov's-Bohm phase, right, you need to have a full circle. So you need to close. So they talk through a quantum dot, and then they split away from zero energy. And based on this shift which you measure, you can say if a state was empty or occupied. But let's say if you would have some kind of other two-level system which would also change its state, right? It could really mimic the signal. So the problem, let's say, which is in current in this field is that let's say if you say, okay, if I want to have a Marana, assume that I have a Maranas, I can do these measurements when I would see this, and this would kind of confirm that it's either odd or even parity. Or I see, let's say, if it's Marana, when I see this signal. So I see this signal, is it Marana? But the problem, but there could be other trivial effects which give you exactly the same signal.
Okay.
So it's very difficult to disentangle. And then you can talk maybe about some probabilistic stuff. But as soon as you consider interferometry and you consider that you have something which changes when you apply flux, then it's not spectacular signal. So anything changes with the same periodicity, it's Aromov's-Bohm effect. So it's not very confusing. And this is what kind of, as I said, so with go condensed matter system, I said like quantum dots or Andreev spin qubits, superconducting qubits, usually you can have some interface, right? You try to confine the quantum dot by gates, and then you're very sensitive to any fluctuations of your electric field on the gate because it immediately shifts your levels. And the idea, let's say, for Marana fermions, it would not happen. And for Marana fermions, there are several platforms which were proposed. So one of prominent is proximatized Rashba nanowires. Now with 1D channels, you can also do by leaving just some empty space between two superconductors. There are magnetic atoms on superconductor when you can collect 1D channel, or you can use some H states of topological insulators. So there are several proposals how one can realize it in condensed matter. So one of example, as I said, what you need is usually you need to specify ingredients. And in this case, we need to have superconductivity. We need to have this one-dimensional channel. And we want to consider, let's say, that we have spin-orbit interaction. So we have these two parabolas, which are split. So one is spin up, another is spin down. We apply superconductivity, and superconductivity generates this symmetry. It opens a gap at the Fermi level. And then we apply magnetic field with additional way to open a gap. Right? It also opens a gap at k equals 0. Now we have a competition between magnetic field and superconductivity. And the idea that, let's say, if magnetic field dominates, when we enter the topological phase, and then observable should be that you have this 1D channel, and you have two Marana fermions at the end, on left and right. And you should see it as a zero bias peak. But the problem here in condensed matter is usually, let's say you have a Hamiltonian which you want to have, but quite often you also have effects which you do not want to have. Right? Because we cannot separate, we cannot control environment. And usually one of the parameters which happens here is how strongly this 1D channel should talk with bulk superconductor. So from one point of view, you want to have very good coupling because you want to introduce proximity superconductivity, which does not occur with nanowires. But when you would see that, let's say, you change the parameters, how strongly these two systems couple to each other. So then you can see, okay, the more you couple, the stronger is superconductivity, which is good. But at the same time, you have another important parameters as spin orbit interaction and G factor, and they go down. And in reality, you want to have both strong delta and strong G factor and spin orbit, but their dependence on strength of coupling is kind of going in opposite directions. And this is a challenge, let's say, for experimentalists. You need to be usually really a very small window of parameters, where in principle you can work out that you can enter topological phase, right? Because also position of a chemical potential and everything. But let's say this is the first experiment with Maranas, which comes from 2012. And this is what people have shown, right? How would you see an experiment? So you look, let's say, in transport data. And usually if you have a state at given energy, you can easily drive transport through it, right? So you have a channel, you inject electron on one end, you pick up it on another end. And if you have no states, then you cannot drive transport. And then you have basically no signal. And this is what we see here when you have these blue areas is where you cannot drive current. And you have red areas where you can drive a current. And this is what we call a superconducting gap. So if you have something like this, you can say, oh, I have a gap, everything is nice here. And then you start to change magnetic field, and similar to what theory predicts, in principle, you should have a bound states, and this is what you can see here. There's some blurb at zero energy. And it's very unusual for condensed matter systems, was I think the first time people observed that you have this blurb, and it does not move as a function of magnetic field. So what was usually kind of observed in majority of experiments in superconductors, semiconductors, when you have a bound state, you apply magnetic field. Let's say that here you see this typical linear dispersion. This is what you would expect from bound states as a function of magnetic field. And here we kind of find out, wow, there's something which does not move, and we have not seen it before. And it kind of, similar to theory, it appears that some finite value of magnetic field extends to some range and then miraculously disappears. But definitely you can see that there's something at zero energy in the middle of a gap. And this was kind of considered the signature of Majorana's. And it looked like very promising for the field, but already when in 1 year later, or even when paper was submitted, not yet published, let's say, we had run the simulations. In theory, what we can do, right, we can run simulations, we know all ingredient, we know what is inside the system, and we have shown if you have a disorder in the system, you can basically get the same type of a blurb, right? But here it has nothing to do with Majorana's, it's basically a disorder effect. Because zero energy, special energy at magnetic field, so basically due to disorder, you can get here, there's actually many states, it's not even single degenerate, it also extends through the entire gap. So it has no characteristics of Majorana's, but in transport, it could look quite similar. And then there was, you can see, a bunch of work trying to discuss if how to kind of an experiment, is it Majorana, not Majorana, is it disorder effects or not? Because what we have shown in my group, basically what you can see in every experiment, that let's say you cover wire by a superconductor, you always have a normal section, and this normal section is not gap, and you can get rise to additional bound states in the spectrum. Right? We can solve it analytically, numerically. We can see that indeed we can get the bound states inside the spectrum, which would look also that you increase the Zeeman field. And then this field goes to zero, right? And then you get this energy of a bound states also stays close to zero for some range of magnetic field. But here from theory, we can 100% guarantee that this state has nothing to do with Majorana or topology. It's just due to the additional symmetry in the Hamiltonian, it kind of likes to also pin to zero its special energy. But if I would do now a transport experiment, I would see these bound states. I can really be misled and interpret as a Majorana fermion. So this is kind of a clean system here. And similar kind of experiments were analyzed, and people saw the zero bias peaks, and we can see that, okay, in experiments they claim the stability because say zero bias peak stays over some range of magnetic field, but at the same time we can also do it in with a bound state. So the spinning to zero energy state, staying stable for some ranges, is not a good signature. This was what acknowledged. So it could occur due to disorder. It can also occur in a clean system due to just some Andreev bound state physics. And this is what Microsoft did, right? They wanted to kind of to improve and develop some protocol. And following the geist of time, they wanted to have something which is unbiased. So it's not that you experimentalist who searches for it yourself, but you want to generate data. When you generate data, you put into some program, and that program analyzes for you and tells you where the topological area is, or you have it or not. And this is example of such kind of analysis. What you do, let's say in this diagram, you look at the data. First, you said like everything which interests us should be gapped, so you can easily. And you try to tune in the topological phase, let's say by tuning magnetic field and voltage, right? So at each point, you can look at it, you can ask, is your system gap or gapless, right? If it's a gapless, it's definitely not interesting because a system should be gapped. And then you can ask if you have zero bias peak inside or you don't have a zero bias peak inside. And if all comes together and you say, okay, you are gapped and you have zero bias peak inside, then you have this area, which is here orange, and you can say, oh, this is a topological, right? And then you can train your algorithm, you can do some numerical simulations, you produce the data, you kind of fine-tune it, and afterwards you can put real experimental data and try to see if you satisfy this criteria or not, right? And the idea, let's say, when this Microsoft preprint appeared, they said, okay, there will no false positives. So this algorithm 100% sure, there's no problem if it identifies something topological, and it should be topological. And this is what we did in our group. As I said, we already proposed some examples when bound states could occur, let's say, due to some local disorder or Andreev bound state physics, basically give already by eye very similar signatures, and the question can be full of a protocol, which seems to be more stringent. And this is what we have done. So we actually identified a system which was definitely trivial. It did not have spin-orbit interaction, so no way that it could be topological. And then we basically put the data from a protocol, and the protocol found the topological states, identified them, and this is definitely false positive, because as a theory, you can just basically take your data, you can look wave functions, you can say if it's trivial or not. And this means that even the kind of a protocol which is designed is not kind of foolproof. So it's a good kind of signature. So let's say you would not try to see any topological physics if this protocol did not find that you're in topological phase. So this is a basic minimum that you should satisfy. But if it's satisfied and it tells you, okay, there's a gap, there's zero bound states, it does not yet mean that it's topological. There could be also trivial states which give you the same reason, right? And you can find such kind of many examples. But still, kind of Microsoft did the progress, right? They have claimed that they see some signatures of topology. They had the second preprint. But there, let's say in the communities, there's also discussions because you don't see the clear gap in this data. Because before I showed you, you can see the problem. Let's say if you have no gap in transport, you can say, okay, should be topological. So gap is kind of a minimum requirement. But if you look at transport data, it's very difficult to resolve the gap. And from this point, you can say, okay, there should be no well-localized Maranas, definitely not protected, because even if you kind of miraculously in topological phase, they would talk with each other, so they would not already satisfied ideas for the qubit. And there was also a lot of discussions about this preprint and how to identify them. Maybe I would go there. So sometimes there was also differences, let's say, with how to provide and reproduce around this Microsoft paper. I think one of the problem why it was so much also media and excitement in the community that some of the data of Microsoft were not published. So for example, we don't know which Hamiltonians they simulated. They do not reveal some data, and this of course made it difficult for theorists to discuss. Or in some cases, we needed to take it as granted that something was checked, or which ingredients were in the Hamiltonian, which properties were studied. But this was part of a problem. And this, I think, at the end, maybe I'll also say, conclude what you mentioned, that there's already interferometer experiment published in Nature, right? When the people, they try now to read out the parity of these states, when as I showed that you have this topological nanowire, you have two Maranas on left and right, let's assume, when you couple to a quantum dot, and then you have a flux through, and then you change your flux, you can see how the state evolves as function of time. You can read out the state, and then basically you see that you have two values of quantum capacitance, which you can identify with two parity states. So in principle, it was supposed to be a measurement of Z gate, or measurement of parity of a qubit. But this paper is published, but even editors, let's say, they confused that the editorial team points out that the results do not represent evidence for Marana zero modes in reported devices, and they present more like architecture. So I assume that we were lucky, we had this nanowires, they had, when this would be a way how to read out, but it was result of review process that referees raised some concerns, and it was kind of by editors concluded that it's not final proof as a part of evaluation process. But we feel this definitely, this paper is already data like 2 years, 1.5 years old, so I'm sure that so far there will be more progress in the field. They tried also to measure X and Z and several qubits and parity readout. But this is very challenging experiments, and the interpretation is not always unambiguous. Because I said, like, you can always say, oh, if it's topological, I should see this signal. But it's difficult to guarantee our way around that if you see this signal, that it could only be topological. And this is like a difficulty of this field. Let's say such questions usually were not arising for our qubits. Right? When people measure, I don't know, superconducting qubits or spin qubits, you do not discuss if this two-level system exists. So this stands on very strong foundation. And how to detect, we don't fight about the existence, or no one kind of misrepresent something else for such physics. But here, of course, also fundamental physics is very exciting, right? And this is why we work in this field. I think I stop here and I would answer your questions.
Thank you. Yeah, thank you very much for the nice talk. What in your opinion, what evidence you would like to see in order to confirm is marijuana?
Yeah, I think there's a lot of fight in the community, right? There's kind of few properties which are predicted, right? In principle, let's say that you have, I think the problem, let's say with current experiments, it was the problem for, I think, all platforms that people did not see a good gap, right? So we know from theory the minimum what you need in order to get localized state is to have well-defined gap in the spectrum. And so far this gap is very small because you have a superconductor, you work at large magnetic field, it kind of reduces your superconductivity gap is not well observed, right? This will be kind of a minimum requirement to fix. And then I would say like the only like most probably experiment which would satisfy people is really to go for definition and to show braiding.
Okay.
Because when you have a zero energy bound state inside the gap, it could be still a standard fermion. Right? And these braiding experiments, of course, are very much challenging also from experimental point of view. Because as you can see, even in Marana, in Microsoft approach, I think at the moment they do not want to do real braiding. They don't want to move these particles, but they want to do so-called measurement-based computation. Right? So that you can say, okay, you have states, you measure them, there's kind of a schemes how you can run it, but they don't want to move it because it's very difficult. Let's say when you have a superconductor, you have nanowire covered by superconductor, you cannot change magnetic field locally, it's impossible, right? They usually apply global magnetic field. And you need to change gates locally. But this is kind of not a problem by itself. This is, let's say, how spin qubits operate. Usually you have a lot of barriers, you switch on, off some couplings. This is not a problem. The problem that you have here is superconductor, and superconductor is kind of ideal metal. So everything you try to change chemical potential, superconductor screens a lot. So that's why, let's say, after you put a superconductor, to have some kind of to move something below in a controlled way and arrange your chemical potential such that you never go out of a topological phase due to disorder seems to be like unachievable in the current stage.
I see. Okay.
And from this point of view, it's kind of a little bit also like, even if you talk with people from Microsoft, let's say what they want in order to make their samples better, and they say, okay, the quality of substrate materials should be better. So disorder is still too large for them, what they have. And they have improved the quality of material over 10 years, tremendous. So this you can see not only in topological experiments, but also for Andreev. There's many interesting physics on these samples which could be done due to this progress on how these samples could be made. But the strategy, let's say, we started from beginning with topological systems because they will be protected from disorder and local perturbation. And now we're kind of in a stage which are the only qubits which are basically killed by disorder. Right? So the level of disorder which, let's say, spin qubits can handle, at the moment cannot be handled by topological qubits. So this is a problem.
I see.
So
Okay.
it a lot depends on material. So it needs to get better. But braiding most probably would be the best proof.
I see. Okay, thank you very much. Okay, maybe let me stop the recording and then see.